In the earlier lectures, we've been talking separately about the translational symmetry of a lattice and the point symmetry of the objects that go into the lattice. In this lecture, we're going to put both of these things together, translational symmetry and point symmetry, to make something called space group symmetry, which is the symmetry that we use to describe crystals. Okay, so just to review some of the things we've talked about up to this point, remember that in 3 dimensions, there are 14 different Bravais lattices. And there are 32 crystallographic point groups. When we combine these two together, we come up with 230 space groups. If the math represented on this slide is not obvious to you, that's okay. Obviously, 14 times 32 is not 230. Well, yes, but of course we can't have every single crystallographic point group with every different Bravais lattice. Remember that each point group is associated with a specific crystal system. So if the point group is 222, that means the crystal system must be orthorhombic. Now you might look at this and say, from this I would expect 32 different space groups. But remember that we can have more than one Bravais lattice per crystal system. So in the orthorhombic crystal system, we can have a primitive orthorhombic lattice, we can have a body-centered orthorhombic lattice, a face-centered orthorhombic lattice, or a base-centered orthorhombic lattice. But even if we do that, at most you would say 4 times 32, what is that? 128. That's still not the right number of space groups. And furthermore, in the other crystal systems, we don't have all 4 possibilities of lattice centering. So yes, in an orthorhombic crystal system, we can have all 4 kinds of lattice centering. But you can see in the other crystal systems, we have less than that. So obviously, this does also not tell us how we might get to 230 space groups. So to understand how we combine translational symmetry and point symmetry, let's look at how we might generate the monoclinic space groups. So as we can see on this slide, there are 2 different Bravais lattices in the monoclinic crystal system. We have a primitive monoclinic lattice and a base-centered monoclinic lattice. And if we were to go back 2 slides earlier, you would see that there are 3 different point groups that belong in the monoclinic crystal system. We can have point group 2, where we have a 2-fold rotation axis and the identity. We could have point group M, where we have a mirror plane and the identity. Or we can combine those and have point group 2 over M, where we have a 2-fold axis, a perpendicular mirror plane, an inversion center, and the identity. Now, if we were just to combine these point groups with these 2 lattices, it should be kind of obvious to you that we can generate 6 different space groups. There are 3 space groups that go with the primitive lattice, P2, PM, and P2 over M, and then an analogous set of 3 that go with the base-centered Bravais lattice, C2, CM, and C2 over M. These 6 space groups are called the symmorphic space groups because the elements of symmetry that are present are only those that come from the Bravais lattice and the point group. You might think, well, how could I get a different kind of symmetry? Well, what's excluded in the symmorphic space groups are those symmetry elements where we have a combination of a point symmetry operation and a translation, specifically glide planes and screw axes. Now, if we are going to introduce the possibility of glide planes and screw axes, then you see we can get additional space groups. So let's put our symmorphic space groups over here on the left. And now let's think about what other kinds of space groups we might generate with glide planes and screw axes. And those are going to be called the non-symmorphic space groups. So if we start with just the primitive lattice, we can replace the 2-fold rotation axis with the 2 sub 1 screw. So we can have P2 and we can have P2 sub 1. We can replace the mirror plane with a glide plane. So we can have PM or PC. When we come to the point group 2 over M, there's actually 3 different permutations we can make from introducing either a glide or a screw axis or both. That's P2 over C, P2 sub 1 over M, and P2 sub 1 over C. Then if we take these permutations and apply them to the base-centered Bravais lattice, we generate another 5 space groups. So at this point, we have 16 different space groups. Is that the complete list of monoclinic space groups? Well, almost, but not quite. Because if you go and look at the list of monoclinic space groups, there are 3 in our list of 16 here that you will not find. There is no C2 sub 1 monoclinic space group. And the reason why is that when you have a C-centered lattice and you have a two-fold rotation axis, those two symmetry elements together generate a 2 sub 1 screw axis. So if you have space group C2, you're going to find that you have both two-fold rotation axes and 2 sub 1 screw axes. So C2 sub 1 and C2 are not different from each other. They're the same space group. So we're only going to use one of them. That's the C2. And then the same logic goes for C2 sub 1 over M and C2 sub 1 over C. Once we eliminate the duplicates, we would find there are only 13 monoclinic space groups. Now before moving on, let me show you explicitly what I mean by the C centering and the 2 sub 1 rotation axis generating a 2 sub 1 screw. So let's take a projection of the C2 space group, and here we're looking down the C axis. Okay, so the B axis is running horizontal in this drawing. Now, in a monoclinic space group, by convention, we're going to put the rotation axes or screw axes parallel to the B lattice vector. So that arrow represents a two-fold rotation axis that's running parallel to B. I've just put a little symbol here, a Chinese character, that we're going to now operate on it with the different symmetry elements present and see what we generate. Let me just point out this little circle here at the center. That is the equivalent lattice point that makes this a base-centered lattice. Okay, so first, let's operate with the two-fold rotation axis. And so that Chinese character gets rotated and represented over here. Now, let's use our C centering, our base centering, which says that all of the lattice points have to be equivalent. So if these two characters are located as they are from this lattice point, we have to have exactly the same thing at this lattice point. Now that would also correspond to taking the XYZ coordinates, the fractional coordinates of each of these characters, and adding 1/2 the A lattice vector and 1/2 the B lattice vector. And when we do that, we will generate these characters that I show here. Now, if you look at that for a minute, notice that I have generated a 2 sub 1 screw axis. This long arrow with the half arrow head, that's our 2 sub 1 screw axis. If I were to take this character, rotate by 180, it would flip over here, and then translate by 1/2 unit cell, 1/2 the B lattice vector, I would put it right back here. All right? But that character was already there. That came about from the action of the two-fold rotation axis and the C centering. So you see, those two symmetry elements together generated our 2 sub 1 screw axis. You'll notice that we also have a two-fold rotation axis here, and that intersects the A lattice vector at 1/2. And I haven't drawn it, but there's also going to be a 2 sub 1 screw axis down here. Okay, so you can see that C2 and C2 sub 1, you can't separate them. They're the same space group, and we call that space group C2. Okay, so all of the information that we need to use these 230 space groups is contained in a reference book that's called the International Tables for Crystallography. And there are several volumes of the International Tables for Crystallography, but we're going to use Volume A. You can access an online version of this reference at the following URL. And why don't we go there right now? I'll show you how to access it. We'll pull up the space group we just looked at, and you can kind of see what I'm talking about. Let's go over the contents of one space group that you might find in the International Tables for Crystallography and kind of see what sort of information we can glean from this reference source. So P21 upon C is probably the most common space group there is. Of all 230, if you were to add up the number of crystal structures in each one, I think this one would be the most common. Now, in the print version of the book anyway, for each space group, there are always at least 2 pages. And here I'm showing page 1 and page 2 for this space group. So let's look at both of these pages and see what they tell us. Okay, so this would be the left-hand page, which I'm calling page 1. And so let's first of all take a look at what the information at the top of this page tells us. So the first thing that we find is the name of the space group. And the name of the space group, there's what's called a long name and a short name. So as I will detail later, and it's different for different crystal systems, these numbers and letters tell us about symmetry elements that go in different directions. So the P tells us that we're dealing with a primitive Bravais lattice. Then we have 1, 2 sub 1 over C, 1. And for a monoclinic crystal system, that's telling us about the symmetry elements that are associated with A, B, and C lattice directions. So in both A and C, there is no symmetry element. So we just write a 1. That's just the identity. But in the B direction, we have a 2 sub 1 screw axis that is running parallel to the B lattice vector, and then a perpendicular glide plane. And this divide by symbol means that the plane is perpendicular to the axis. Now, every single monoclinic space group, all 13 of them, have no symmetry elements in either the A or the C direction. If they did, they wouldn't be monoclinic, because we can only have a 2-fold rotation axis or 2 sub 1 screw axis along one direction. So it's a little bit redundant to have the 1s. And so in the short name for this space group, we drop those. And it just becomes P 2 sub 1 upon C. What else do we see? Well, this C2H5, that is the Schoenflies name for this space group. Remember that the Schoenflies symmetry elements really just tell us about the point symmetry. So this space group has C2H point symmetry. And the 5 tells us it is the 5th space group that has that point symmetry. I cannot think of any time that I've ever actually used this name for the space group. So in general, we don't have to worry about that. What else? Well, over there on the right, we see the crystal system. This is a monoclinic crystal system. The 2 over M, that is the point group symmetry, which is given in the Hermann-Magwin notation. We don't write out the Schoenflies point group, but that comes directly from the Schoenflies name of the space group. Yeah. So 2 over M in Hermann-Magwin symmetry is the same as C2H. All right, so that's the kind of information we can get from the top of page 1. Now let's take a closer look at what these drawings below it mean. So this is kind of like an architect's drawing. Remember that our unit cell here in a monoclinic crystal is going to be this parallelepiped, this 3-dimensional box with parallelograms for each face. And in a monoclinic crystal system, the A and C axes don't have to be perpendicular, but the B axis is perpendicular to both of the other axes. So when we look here in the upper left, this is a projection of the unit cell looking down the B axis. The drawing right here below it, this would be as though we folded the lower face of that parallelepiped down. And so this is a projection looking down the C axis. And then the drawing in the upper right is a projection looking down the A lattice vector. Okay, now at the bottom, where it says symmetry operations, in this point group, we have 4 symmetry operations. An identity, a 2 sub 1 screw, a C glide, and an inversion center. And each symmetry operation in the space group is represented here. So let's see what these mean. Number 1 is just the identity. So, okay, that's got to be there for mathematical reasons, but otherwise we're not too worried about it. Symmetry operation number 2, that is our 2 sub 1 screw axis. How do I know that? Well, I see that I've got a 2, and that symbol means that there's a twofold rotation. And then the parentheses 0, half 0, that's a translation. That tells us we're going to rotate by 180 and then translate by 0, half 0, 1/2 of the B lattice vector. The other part here, 0y 1/4, that tells us where in the unit cell this 2 sub 1 screw is located. Parallel to B, so it really doesn't have a coordinate along the B axis, but in the AC plane, it's at 0, 1/4. Now, if we go look at our drawings, let's say 0 in A and 1/4 in C, that would be right here. So this hurricane-looking symbol that's circled in blue, that is a 2 sub 1 screw axis. And we are looking directly down the axis in this projection. If it were just a lozenge, in other words, if it didn't have these tails out sticking beyond it, then it would just be a twofold rotation axis. And so we can see that when we look down the projection of the unit cell, we can see 6 2 sub 1 screw axes. Now, in the other projections, because the screw axis is parallel to the B lattice vector, in the other projections, the 2 sub 1 screw axis is lying in the plane of the projection, or maybe a little bit above or below it. And so in that case, we use these half arrows to denote that there's a 2 sub 1 screw axis running in that direction, but the axis itself is in the plane of the projection. And so we see it here in this projection looking down the A axis, and then we see it also here in this projection looking down the C axis. That 1/4 that's written next to this half arrow, well, that 1/4 means that the axis is sitting 1/4 of the way above the plane of the projection, 1/4 of the C lattice vector. The next thing we're going to look at is symmetry operation number 3. And the 1 bar, that's our inversion center. And this tells us that there's an inversion center at 0, 0, 0. And so the symbol for an inversion center in these diagrams is this little hollow circle. So yes, we see that we have a little hollow circle, an inversion center at the origin, 0, 0, 0 in all cases. But that's not the only inversion center. We also have inversion centers at the center of each face. So that would be at half, 0, half. Here it would be at 0, half, half. Here it would be at half, half, 0. We also have inversion centers on each edge. Okay, so those are not all written there, but those can all be generated by symmetry once we put that original inversion center in. And then symmetry operation number 4 is the C glide plane. Okay, so the C tells you that it's a C glide plane, and then the X 1/4 Z tells you that it's in the AC plane, and it crosses or intersects the B lattice vector at 1/4 of the way along the unit cell. Where do we see the C glide in these drawings? So in the projection that's in the upper left, looking down the B axis, the glide plane is actually in the projection that we're looking at. So we see the entire glide plane when we look down this direction. And so we've got this symbol here, which means that, okay, yes, there is a glide plane in this projection. we can see the 1/4 tells us it's 1/4 of the B lattice vector above the projection we see. And then the arrow there shows us the direction of the translation part of the glide. And that is parallel to C. That's why we call it a C glide. In this projection in the upper right, we see this dashed line. And we can see that there's actually 2 glide planes in the unit cell. One that cuts the B-axis at 1/4 and one that cuts the B-axis at 3/4. The fact that it's a dash tells us that the translation part of the glide is in the plane of the projection. And you can see here is the C lattice vector vertically. So if I were to have an atom here, I would mirror and then translate it down to something like here. Okay? And then in this final projection, in the lower left, now we have a dotted line that to represent the glide. And why the different symbol? That's telling us that the translation is actually out of the plane of the projection. So here, if I were to have, let's say, an atom right here, I would mirror, and then I'm going to translate by 1/2 C. But in what direction is C? Well, C is out of the plane of the projection up toward us. So that's why we have a different kind of line to denote the glide. If you had a mirror plane here instead of a glide plane, those dashed lines would just be solid lines. And that symbol up here, this thing, would look very similar, but it would not have an arrowhead at the end because there's no translation associated with it. So this kind of drawing tells us where all of the symmetry elements are within the unit cell. And the symmetry operators at the bottom are the mathematical representations of the different point symmetry elements that are in this space group. Now, if we go to page 2, what you can see is something very different, but in some ways actually even more important for us. And the most important thing we see on this page are what are called the Wyckoff sites. So let me talk about this top one first of all. This is site 4E. And what does that mean? Well, the 4 is the multiplicity. So this site, the general position, tells us that if we just were to plop an atom into that unit cell, just at some arbitrary place, not on any particular symmetry element, that we are going to generate 3 additional atoms. Right, so this atom is the one that would be generated by the 2-1 screw. This would be the coordinates of the atom generated by the inversion center. And this one would be the coordinates of the atom generated by the C glide. The other Wyckoff positions, you see, have a different multiplicity. They only have a multiplicity of 2. So maybe the easiest one to envision is Wyckoff site 2A. So that Wyckoff site is located at the origin, 0, 0, 0. If we put an atom at the origin, let's say we put a carbon atom, then this tells us we will, by symmetry, get another carbon atom at 0, half, half. These are the fractional coordinates of where within the unit cell it's located. Why only 2 atoms? Well, let's go up to our general position. Let's make x, y, and z 0 and see what happens. Well, position 2 is at minus 0, 0 plus 1/2, minus 0 plus 1/2. That's 0, half, half. Generator 3 would give us an atom at minus 0, minus 0, minus 0. Well, that's the same thing as 0, 0, 0. And then generator 4 would give us an atom at 0, minus 0 plus 1/2, 0 plus 1/2. Well, once again, that's 0, half, half. So the way you can think about that is if you put an atom at the origin, the inversion center is not going to move that atom at all. It's just going to generate the atom on top of itself. And then generators 2 and 4, which correspond to the screw axis and the glide plane, they do generate an atom in a different place in the unit cell, but they both map the atom to the exact same place in the unit cell. That's what we mean by a special position. It'll have a smaller multiplicity. If we put an atom at 0, 0, 0, there's only going to be 2 of them in the unit cell. Also, we see here this thing 1 bar. That tells us the site symmetry of an atom on that Wyckoff position. So it tells us that the atom is sitting on an inversion center. And that information can be useful sometimes, especially for things like spectroscopy. Okay, so in this particular space group, there are 4 general positions, each with a multiplicity of 2, each on a different inversion center. The A, B, C, D, that doesn't have a real meaning other to say that they're different from each other. Okay, so Wyckoff Site 2B is located at a different place in the unit cell than Wyckoff Site 2A. Right, so all space groups will have a general position, and most space groups will have multiple special positions that have lower multiplicities. Over here on the right, we have what are called the reflection conditions, and I'm not going to spend too much time on those. Those are for when you do diffraction. This tells us which kinds of lattice planes give rise to diffraction peaks. So that's all I want to say about it, but if anybody's curious about that, we can talk about it some more. The next and the last thing I want to talk about is what comes at the bottom, which has to do with subgroups and supergroups. So let's talk about subgroups first. A subgroup would be a different representation of the crystal with some of the symmetry gone. The maximal non-isomorphic subgroups, those can be divided into type 1 and type 2. The type 1 non-isomorphic subgroups have the same translational symmetry. Basically, they have the same size and dimensions of the unit cell, but they have fewer point symmetry operations. So what this says is if we only keep point symmetry operations 1, that's the identity, and 2, which is the 2 sub 1 screw axis, but we lose the other 2, the space group symmetry would be lowered to P 2 sub 1. If we only keep the identity and the inversion center, the space group symmetry is lowered to P1 bar. That actually is a triclinic space group. And if we only keep point symmetry operations 1 and 4, 4 being the glide plane, the symmetry becomes PC. In higher symmetry space groups, there may be many, many non-isomorphic subgroups like this. Here we don't have any non-isomorphic subgroups of type 2. Those are ones where we keep the same point symmetry, but we lose translational symmetry. So if we had a centered lattice, we might go to a primitive lattice. That would be a non-isomorphic subgroup of type 2A. Or sometimes actually the unit cell will actually get bigger, and that represents loss of translational symmetry. So supergroups are just going in the opposite direction. For example, here we see minimal non-isomorphic supergroup type 1, and we see PNNA. So that's just telling you that you could lose certain point symmetry operations from PNNA, and you could wind up at this space group. The subgroups and supergroups are quite useful if you're thinking about phase transitions or maybe relatively subtle distortions of the structure driven by, I don't know, sometimes electronic instabilities or sometimes other things.